baked in, and she was a presenter. So it's like, hey, he's downtown. And so she said the whole thing.
It was really this one.
Yeah. I know. It should be good. It should be awesome. Yeah, she was like super into it. She runs an art user group, like meetup. So she's like, does this stuff. She also has sports.
Definitely will need help. Maybe don't send it.
Natural image sciences.
Okay, that's fine. Yeah.
So let's get started. So just as we're all getting settled, so let's start by reviewing the schedule. So we're starting a new section on sort of regression. It's actually regression and like dimensional reduction kind of put together in. We'll kind of go back and forth between these in the lectures. So the first couple of lectures, so the one today and Wednesday, are I'm going to go over like all of like basics of linear regression today, and then all of Wednesday the basics of kind of PCA and SVD based so dimensional reduction, and so these are going to be pretty fast lectures. I'm going to go through a lot of material. I'm going to kind of somewhat assume that a lot of you have seen this before. I know some of you have not, but a lot of you have. And so there are links to this other text I wrote for kind of a class that would come before this that are linked off of here that have much more thorough discussions on least squares, so least squares regression, and also so dimensional reduction with SVD and PCA. So we'll go through those, but these are going to move pretty quickly. So if you need more background, those links I think are fairly good resources. I still haven't finished the notes, that's why I haven't shifted the schedule, but I'm going to probably shift from here everything down one lecture, so the matrix sketching will come after the midterm, and then this will move down here, and then this lecture will get replaced by a bunch of small modules elsewhere in the semester. I'm going to add in a lecture on on metric learning, which is something that a lot of students end up needing in their projects. So I haven't finished the notes for that yet, but that'll probably go in there. The midterm will stay on the same date. I'll fix that. Okay, and then the clustering assignment is due on Wednesday. So a lot of you have been asking questions. I've been replying on Canvas, so that's a great place to ask questions. I won't be able to take questions after class today. I have to leave for a meeting at 4:30. That's across campus. But please ask questions on Canvas. I'll try and get to them very quickly. Again, the question 4 on the homework is a little bit open-ended, but hopefully it's fun as well. So okay, any quick questions on the homework? Okay, so one other thing I wanted to mention, there's an event with the Data Science Club that's happening tomorrow, 5 to 6 p.m. and it's going to be hosted by one of the data scientists at Stack Overflow, and they're going to be, I think they're going to be talking about some stuff related to PCA, which we'll talk about. I'll just mention it today in case you haven't heard of it before, but then that'll be the kind of the core of the lecture on Wednesday. So I think so it's pretty good timing. So that should be a fun event. So I encourage you all to go. And if you haven't signed up for the mailing list, I encourage you to do that as well. Okay. So let's see. So clustering is due on Wednesday, the Science Club event, and then we'll start this. And then again, please look in this other book, the link text, if you want more information on this. But we'll kind of go through it. So we'll kind of go through this quickly. All right. So the core of this, we're going to start with the first part where we're actually doing prediction here in class. And we're going to be dealing with data which eventually will be in high-dimensional data. But the lecture today will basically be, everything will mostly be in 2 dimensions, so I can draw pictures like this. So on the, let's see, so on the input of this problem, I'm going to have a data set P, and this is maybe a little bit strange notation, but it helps me generalize it a little bit. We're going to have data points P1, P2, up to Pn. And so in general, we're going to have that each Pi is going to be in some d plus 1-dimensional space. But today, we're going to have Pi is going to be in R2, and this means that we can think of each Pi as being an xi scalar and a yi scalar. Right? So each P is a data point. In 2 dimensions, that means I can draw them like this, right? So this is P1 equals x1, y1 here. Okay, so I have these data points. I draw them in 2 dimensions. And in general, the x variables will be explanatory variables. The y will be these dependent variables. And the kind of the goal of the lecture today is then to fit some line which kind of is going to go through this data. Okay, we're going to find a line that kind of goes close to the data. In general, we're going to generalize it so that this will stay in R, so it's a scalar value, and this will be in RD. So this x dimension will actually eventually be d dimensions, but we're going to have 1 dimension y. So these are going to kind of explain what's going on, and we're going to try and predict the y value based on these x values. Right? So given this data and this line, what we'd really like to do is we're going to have the idea of having some new data where we only get the x coordinate or x coordinates. And we want to try and guess. So this is the guess of the y coordinate. Okay, so the goal of all this is on new data where you only get the x value to predict what the y value is going to be. And this line tells us how to do this, right? If we fit a line through the data we have, then when we have a new data point, we can guess, okay, it's going to approximately be on this line. And this is kind of the whole point. Hopefully this is not an unfamiliar thing. Right? So who's seen this linear regression problem before? And is this new to anyone? Oh, okay, good. Okay. And so just to kind of, I'm going to go through stuff and define stuff carefully because maybe you've seen the problem before, but maybe probably don't know everything there is about it. And so in order to do that, for the data, how do we choose this green line, right? So this is the problem. In particular, for each data point, we want to look at the distance from this data point onto this line, right? So each of these data points, we draw kind of this distance onto this line, right? And some of these are pretty small. And so this distance, so if this is pi, then this is ri, is the so this is called the residual associated with this data point. And this is only measured in this y distance, right? I assume that I know the x exactly. And sometimes this isn't a great assumption, but I assume I have this data exactly, and I only care about predicting the y. So for instance, I'm not in this setting, I'm not looking at something like this distance, which is the closest distance onto the line. I'm not trying to minimize that. I want to minimize these pink lines, not this red line, which is the closest onto the line. Okay. When we talk about principal component analysis, we'll be projecting onto the closest point on the line, and we'll talk why that's a different problem in various ways. Okay. But I'm just predicting this vertical distance on the line. And so in general, what I want to do is the goal is to fit a line, I'll say L, which will be defined, so L of x equals A of x plus B, right? And so this distance here is B, and so A has to do with the slope. So A is going to be the slope, and B is the intercept, right? So I'm trying to fit this line through these data points, and I want to fit the line in particular to minimize the sum of the square of the residuals, right? So the goal is to find the arg min out of all of these lines. That is if I sum over all of these data points, I will want to look at the distance from the y value of the data point minus the prediction based on the x value, and I square this. Okay, so I want to find the line which minimizes the sum of the squared distances here. Okay, and I can, this is equal to arg min a b, again, pi, say yi minus a xi plus, so minus b squared, right? So the a and the b is a fixed model that describes this data, so I want to find a and b, so when I sum over all of the data points, I minimize these residuals. This term here is exactly this pink residual here, right? So this term inside of here is the residual Ri. So I'm looking at the squared residuals, which is what I'm trying to minimize. Okay? So I'll come back to kind of, is this the right model for the problem? And we'll see that sometimes we want to tweak this. But let me just tell you about all of the great things quickly about this least squares model for linear regression. Okay, so this is often called ordinary least squares regression. Okay, because it's this is just the ordinary version. We'll look at non-ordinary versions as well. Okay, so this should be a standard kind of formulation. So the nice thing about this, so I'll go through kind of 4 nice things about this. One is that there's a closed form solution. So I can solve exactly for this. I can easily solve for A and B, which optimizes these squares. In order to do that, let's see, I'm going to define P of x bar, which is basically the average of all the xi coordinates, right? So this is going to be 1 over, let's say the size of P is n, so this is going to be 1 over m times I equals 1 to n of the xi values. Okay, and I'm going to define the same for the y values. Okay, and then I can compute the covariance between these px and the py vectors. So these are all the x coordinates, all the y coordinates in a vector. which is 1 over m, well, 1 over n, pi and p is going to be px I minus px bar pyi minus py bar. Okay, so I can compute this covariance. I can compute the variance of px, which is going to be just the covariance of px by itself. Okay, and then with these, I can simply solve for a and b. The optimal a is then the covariance of px, py over the variance of px. This is equivalent to the dot product of px and py divided by the norm of px squared. This is true if I've subtracted out the center. So if I subtracted out the mean, so the average of each coordinate is 0, then it's equivalent to this term. And we'll see something that looks like this in a second. That's what I'll write it up here. And then, so this is the solution for A, and then B is just going to be py bar minus a px bar. Okay, so just the average of y coordinate minus the average here, and this just says so that I'm looking at all of the case when the this is just saying the offset so that it goes through the mean of the data points. Okay, so the point is that there's a closed form solution for this. I can write down, I can calculate these based on the data, and I can write down the optimal A and B. These minimize these here minimize this least squares formulation. So that if I solve this, it minimizes least squares. You probably don't need to write this yourself. There's built-in functions for this in Python you can use, but it's for data sets that are not too large. This is what it's doing, something like this. Okay, so you can solve it exactly in a closed form. I don't know if Gauss or someone came up with this a long time ago, but like they're trying to, this has been known for a long time. This is kind of folklore that one of the reasons why you do this least squares formulation here is because there's this simple closed form solution. You can come up with the optimal solution by just doing these calculations. I don't need to, like if I change this to the sum of the absolute values, it becomes a lot harder to find the optimal solution. Maybe that makes more sense as a modeling thing, but it's, especially before we knew how to do like optimization techniques, they didn't know how to solve for it. So what's the point of writing it down? These squares, you can solve for it exactly. Yeah?
So I was wondering, can you just reverse the problem and try to find all the points that pass through a given line, and choose the line which has maximum quantum?
Oh yeah. Right. So instead of finding the one that minimizes all the sum of the squared distances, you want to do something like find the single line that passes exactly through the most number of points. Right. So we'll talk about some variants of this in this lecture. That's not one of them. There are these techniques called like these ransack techniques, which is used for shape fitting, that essentially tries to do something kind of like this. In general, for this setting, it turns out that turns out not to be a great idea, because a little bit of noise in a data point will cause the line not to fit through it. Even just some imprecision and some rounding errors is going to break this. And it could be that no line passes through more than 2 points. In general, that's going to be the case. If the points have random error to them, then it's a event of measure 0 that you're going to have a line pass through more than 2 points. So then you could skew this by having 3 outliers that a line passes through and no line passes through any of the data points. So what we'll see is that you can actually fit a curve, a polynomial curve through these, that you can fit through all of the points if you make the polynomial high enough. Now it turns out that's not a good idea either, because then you get a really curvy polynomial. So we'll come back to these ideas. That turns out it's an interesting line of questioning. We'll see some alternatives to this formulation, though, that will end up making a bit more sense. Great. Thanks for the question. Okay, so this is the first kind of cool thing about this. There's a closed form solution. The next cool thing is that this extends to x in RD. Extends naturally, including the closed form solution, including the formulation. Right, so this is the only point in this particular lecture where we'll go in higher dimensions. But now we're going to say that the input is going to be, P is going to be x and y, where now x is going to be a subset of R n times d. What this means is, and y is going to be just in Rn. So what we'll think of this as, this will be y and this will be x here, and this will be pi, which is going to have an x vector coordinate and a y value here, and the xi is going to be in Rd. So it's a d-dimensional data point now. So I can think of xi as actually being xi1, xi2 up to xid. You can see that the subscript notation is starting to get a little bit heavy here. You start to get used to these things as you do this, but I want to kind of avoid this when writing on the slides. So I can think of it as this matrix, right? So each of these data points, the x part is a row in this matrix X, right? So X is now this matrix, which is X itself is going to be D by N. X is an N by D matrix. Okay, and so now I can try and predict my line is no longer going to be is now going to be kind of a function in general. So my function, which is going to take in a d-dimensional vector x now, right? So this is now in Rd. This is going to look like B, which we'll call A0 actually, plus J equals 1 to D times X I J times A J. Right? So now I'm going to have D plus 1 coefficients instead. Instead of 2 terms that need to learn, D and A, I'll call B A0, and I'll call, I'm going to have D of these other values A. And this is going to be my function instead of a line. This is still a linear function, but this can predict things that take in a d-dimensional input and predict a one-dimensional value as the output. It's going to look like this. And so I want to find the one, again, that minimizes the goal, again, is to find the arg min A, which is A0 up to AD, and so an associated function f of A, which is going to minimize this function here, where I do yi minus, I'll just call this f of xi, where this is f of A. Right, and this is squared. So I'm still doing the sum of the squared residuals here, but now they're in a higher dimensional space. And so this looks like it's much more complicated. Now I can't do this covariance and variance of these of the inputs anymore. But it turns out there's still a nice closed form solution here. What I'm actually going to do is convert this matrix X. I'm going to handle the offset in some fancy way here. I'm going to go from X, I'll call this X tilde, which is going to be this matrix here, which is going to be, this first column is going to be all ones. Then I'm going to have x11, x12, up to x1d, and this is xi1, xi2, up to xid. So now this is going to be d plus 1 dimensions and by n dimensions. Okay, so I've added a column of all ones, and that will correspond with the offset. I can think I had a variable x0 that's always 1, and I multiply that by a0. Okay, so this is the same thing here. And so then I can again solve for a, which incorporates the offset a0 and b together. Now a turns out to be, there's a linear algebraic solution for this, which is going to be x tilde transpose x tilde inverse. So this quantity inverse times x transpose times y. Oh, this is x tilde transpose. Okay? So this is going to look like the formulation before. If I go back here, it's going to kind of be a dot product over this norm. This is kind of the, I'm dividing this to taking the inverse here is like dividing by, and this is kind of the norm of x, and this is like the dot product part. So it's kind of a similar form here. And by putting this column of all ones here, I can solve for this offset automatically. I can just fold this into here. Okay, so I can go to this higher dimensional formulation, and I can still solve this in a closed form. This is this minimizes this again minimizes the least squares formulation. Okay, so I can go to higher dimensions, and with just a little linear algebra, and of course a little bit runtime increase by factors of d, I can again have a simple closed form solution. Okay, so people have kind of seen this before? Okay, great. Okay, so the next cool thing about this, so number 3, is I can do polynomial fits also basically for free. Okay, so now again I'm going to assume that my input P is going to be a subset of R2, so that means each Pi is going to be equal to Xi and Yi, where again this, each of these is just a scalar value. You can extend this again to higher dimensional values, and I'll let you kind of work that out on your own. But now the goal is going to be a more complex function fit. The goal now is going to be some polynomial function that's going to go to some power t. Let me not call it sub t here. But we're gonna choose some fit here. This will take in a scalar value, right? So let's see. So this function is going to be defined as y is going to be equal to a0 plus a1 x. Right, so this is the same as before, but I can do a2 x squared plus a3 x cubed, right, and in general up to some power t. At x to the power t, right, so this can be, I could write this as sum j equals 1 or equals 0 to t of a0 times x to the power t. Right? Notice x to the power 0 is always going to be 1, so that's how I get this coefficient term. Again, there's this nice kind of trick for handling the coefficients. Okay, so I can fit these polynomial functions. These are going to be things that if I go back to this picture, is going to allow me to do something kind of silly through here that's going to kind of fit through all these points. I can kind of swerve through all these with some polynomial, and the degree of the polynomial allows me to kind of have more terms. Okay? Okay? So I want to solve for this again, and again the goal is to find the R min A in RD plus 1, so this set of these A values that's minimizing all of my data points P of yi minus g defined by these coefficients A of xi squared. Right? So now I'm just replacing this line or high dimensional function with a different polynomial function, still minimizing the sum of the squared distances to the y value. Same as before, but now I have polynomial, so it's a much more curvy function. The degree is high enough, you can go through every single one of the data points. Yeah?
Do you mean that it's A sub j, x superscript j?
A sub, yes, thank you, right here. Yeah, this is A sub j. Thanks. And this is also here. Great, thank you. All right, so this allows me to fit much more complex things. If I have higher dimensions, I can make polynomials that are a function of not just one input scalar, but of multiple input scalars. I can fit much more complex functions, even at high dimensions. You just have to expand all these things out. In order to solve this, there's also a closed form solution. What I do is I just have to regenerate my x tilde matrix here again, which now is going to be 1, x1 squared, x1 cubed, up to x1 to the t, and in general I have 1 xi squared, xi cubed, xi to the t. I create the x tilde matrix in the same way. This is called so this is called linearizing the polynomial. I pretend instead of having a one scalar value input for the explanatory variable, I just have t plus 1 of them now. And each of them I treat as a different dimension, and I do the same solution as the high dimensional version. Okay, so again, there's again a closed form solution the same way as before. Okay, so I get to do all this high dimensional stuff, I get to do these polynomial fittings, they all have this nice closed form solution.
So what's the performance difference if you take your first initial data, find its center of mass, calibrate it so that everything moves, so that the center is the origin, so you can get rid of those ones, versus doing all this and keeping the ones in there?
I don't think it's going to be significantly different. You get, the slowest step is going to be taking the inverse of this matrix. You've increased this from d dimensions to d plus 1 dimensions. It roughly takes d cubed time to do this. Is it d squared or d cubed? I think it's d cubed time. You've increased d by 1, so it might be a little bit faster to center first and do it that way, but not significantly.
But they have the same outputs, exactly?
They should have the same outputs. There might be some numerical differences. I don't know which is numerically more stable offhand. Yeah, I'm not sure. I know kind of if you do this inside of any library, it's going to call really stably and really heavily engineered linear algebra stuff to do it properly, and that's going to ensure that's stable. There may be some noise adds as you do the centering, but it's only one step. I don't think it's a big difference. Yeah, back?
So when you're trying to find A for the polynomial fit,
Yeah.
at what point does it determine what T is?
Yeah, so we'll come back to that. We're going to have to use cross-validation in order to do that. I'll talk about that like in like the noise lecture in class, which is not for like a month. If you look in the other notes on linear regression in the other text I linked to, that talks about it in there. But you'll do cross-validation and do that. And there's unlike with k-means, what is k-problem, there's a much more kind of quantitative way to find the solution than just plotting and looking at about where it is. You actually have a quantitative way to how to choose it. And we'll come back to this, but that's a very important question. You're going to overfit to the data if you choose T to be too large, and you don't want to do that. We'll talk about other ways to deal with overfitting inside, starting in this lecture. Another question?
Are we guaranteed that the inverse exists? And if not, is it okay to do the pseudo-inverse?
Yeah, so if the inverse, you should probably write this as like the pseudo-inverse just in case. And I think that's what's done if you call like, if you could do this, like write this out in Python, or you can call like a linear least squares. I think it generally does something which like reverts to something like the pseudo-inverse. If the data points here are full rank in d dimensions, the inverse is going to exist. And in polynomial, if you live to a d or a t-dimensional space and it's full rank in there, the inverse is going to exist. You know, if you're doing a polynomial degree where you're close to it not being full rank, you're definitely going to be overfitting. If you're getting something even close to not being full rank, you're probably overfitting. You can try and like do this, like Python. Like I remember I was doing some examples where I was trying to get it to fit through all the data sets, and it gets very close to not being full rank, even with data that is, and so it gets confused. And so but you're probably overfitting well before you get there. But, yeah. Any other questions? Okay, there's one more cool thing about this. And this is going to lead us into kind of, it basically says that this is optimal, and then we're going to say, well, maybe it's not optimal. But the fourth cool thing is called the Gauss, so the GaussMarkov theorem. And this says that this is essentially, it says that all of this is the minimum variance solution. So if you want to predict new data and you want to come up with an estimator which will have the smallest variance out of all estimators, then this is it. Assuming that it's going to be an unbiased solution. So you restrict that that means that the expected error on the prediction of a new data point, the expected error is going to be 0. Right? So I don't expect it to be larger than what I predict. I don't expect it to be smaller. The expected error on a new data point is 0. And that all errors, all of these residuals, all the residuals are not known to be so these are not known to be correlated. So basically the assumption that they're IID. All the data points are the x the x value was given to you somehow, and then it gave you a y value, which was somehow IID from some base solution, right? So that, or that they were independent, so that they were given noise from some, whatever the true solution was, but that you don't, that these noises are not correlated anyway. Okay, so you have to make some technical assumptions, but if you assume the solution, you want an unbiased solution, and you can't just, and you don't know any information about some correlation between the noise from the solution, then the least square solution is the optimal. It minimizes the sum of squared errors, which means it's the minimum variance solution. Okay, so this is kind of, there's some theorem that you can prove that this is kind of the best thing to do in some sense. Okay, so not only is there a closed form solution in 2D, there's a nice extension of the closed form solution to any higher dimensional setting. The polynomial succession works, and you get this optimality proof about it. It's the minimum variance solution. Okay, so what's left? If we have all of these things, then in half of a lecture, we've covered everything you need to know about regression, right? Everyone agree? Now, as far as the class last semester, this was all I told you. So turns out that this is not the end of the story. So I want to talk about a few extensions to this that are going to tweak the question a little bit. Some I'll basically just mention in this lecture, and then we won't have time to come back to them in the semester. Others will have whole lectures which are coming back to them. Okay, so the first thing is that what if we so minimize the projection distance instead of the vertical distance. Okay, so this comes back to, if you come back to this picture here, if you remember, if you look up top here, we're always measuring these residuals in terms of just the y dimension. But if I have data that's, say, d plus 1 dimensions, maybe I don't want to make one of the coordinates special. And so then I say, I want to measure the distance to the closest point on the line, or the closest high dimensional point. And this will basically be what PCA approach is about. It turns out I don't need a full dimensional kind of function anymore. I can go to a lower dimensional function and try and solve this. And so the lecture Wednesday will talk about how to look at this. So if I do this projection distance onto the closest point instead of the vertical distance, then this is this is PCA, the PCA model. So this is kind of a different model for fitting linear subspaces through data. There are polynomial and kernel extensions to this the same way there is for polynomial, for these regression fittings. We'll talk a little bit about this on Wednesday, and then more about how to scale this up and other variants of it kind of in some other lectures. Okay. So one other thing that we won't talk about so much here, but that X transpose X inverse can be expensive to calculate. If D is really big, then sometimes this can be expensive. And it also makes it tricky. I need to have all the data in memory at once. It's not just expensive in terms of runtime, but if the data set's really big, then I have to kind of compute, I have to have all the data available to me at once in order to do this. So there's going to be like so there's some versions of stuff like this that works with streaming data, and also stuff that we won't talk about in this class, but is more of kind of a topic that fits in with the machine learning class. It is in the lecture notes. You can do these stochastic gradient descent approaches to solve this as well, where you don't need to look at all of the data at once in order to solve this. This turns out to kind of magically be a little bit more robust to noise. as well. So in really large data sets, you want to use one of these different models. We'll talk some version of these streaming versions, but we won't talk about that SGD stuff in this course. Okay. The third thing we'll talk about, and I'll just mention this in this lecture, is so I want to minimize so something other than the sum of the residual squared. So I want to do something other than minimizing the sum of these residuals squared. One variant is just minimizing the just the sum of the residuals. This turns out to be, you can write it down and you plug it into like a linear solver. It's not very exciting. I'm going to kind of I'm going to give you an example which is completely different formulation. That's going to be a robust estimator. Okay, and so this will be the Thiel-Sen estimator. And so this is a completely different way of trying to fit a line through data that's going to be incredibly resistant to outliers of the data. Okay, and it's not going to really optimize something. It's going to be, you calculate stuff with the medians of various quantities, and that gives you the estimator. So it's a completely different way of doing this. Instead of minimizing sum of squared errors, sum of squared has an issue that if you have one outlier, it can pull stuff really far away. So that seems like not great. So other than having a closed form solution, this is kind of a weird kind of choice to make. Mathematically, it's really nice, but modeling-wise, it seems like sometimes it's an odd choice. And then the fourth thing we'll talk about, and we'll talk about it some in this lecture, and then we'll come back to it maybe after fall break. That will be to look at some biased solutions. Okay, so remember that this was the optimal, assuming that it's unbiased. So that means, it turns out, these assumptions for the GaussMarkov theorem are actually, about the optimality, are not something just to dismiss as being technical things needed for the proof. You can actually have a lower variance solution by having it be biased. If you add some bias into your solution, you can reduce the variance of your estimate. That means you can have a smaller expected sum of squared errors. That seems kind of wild. It turns out that there's a really simple way of doing it. That you kind of just change, you can actually change the closed form solution in one sense, just a small amount. So it's still a closed form solution for all these magical things. And it will give you a biased solution, and if you do it the right way, you lower the sum of squared errors. And so we're going to talk about these with regularization. Okay, so we're going to add what's called a regularizer term to the formulation, and this regularizer will give us a little bit of bias, and in some cases won't make it that much hard to solve. In other cases, we're going to give other magical kind of sparsity effects. Okay, so the ordinary least squares stuff is all very cool, but it's not the end of the story. Okay, so I'm not going to talk anymore. PCA we'll talk about starting Wednesday, and then this we'll talk about some of this later. So I'll talk about this now, and then we'll spend the rest, just fairly briefly, and then we'll spend the rest of the time previewing this, and then we'll see how to do the L1 version in a lecture later on. So we'll have another lecture on lasso, which is a weird name for one type of this regularization. All right. Okay. So the Thiel-Sen estimator. Okay, and so to start off, let me say, before I define what this is, let me just tell you what the breakdown point of a data is informally. The technical definition is kind of is messier. So the breakdown point of an estimator is is basically the largest fraction of data points which can be arbitrary outliers, and the estimator is still okay. Okay, so the technical definition is much more complex. So I'll just say it like this. But the classic example is that the mean of a data point, you take just the average of the data set. If you put one outlier, it can make the mean move very far away, right? So if I have a data set here just in 1D, right? And I have one data point. This is an outlier, right? So if the true mean, this is what the this is what a good model of the data would be as a single point. But with an outlier, but the mean may be outside of this data set, right? The mean may be pulled outside of kind of where this data is by a single outlier. Whereas if instead I took the median of the data set, it's still going to be in here. One outlier can't pull it arbitrarily far away. So the mean has a breakdown point of basically doesn't have a well-defined one. It basically goes to 0. But the median has a breakdown point of what's called of 1/2, which is the best possible. It's actually kind of has to be slightly less than 1/2, but in the limit it's 1/2, right? So I can move everything just up to 1/2 of the points out to this outlier, and the median will still lie somewhere in here. It's still going to be okay, right? And those outliers can be arbitrarily far away, and it doesn't break down. So the ordinary least squares has the same problem as the mean, in that one outlier can completely distort the model. Okay.
For the median, doesn't that require like half of those outliers to be like on one and the other?
Yeah, the worst case is they would have half of the outlier. All the outliers are going to be all the way out here. Now I can have, say I have 100 data points, I can have 49. I can move 49 of them out to this outlier point. 51 of them will be here, and the median will still be like basically at the 51th point. But it'll still be kind of okay. It's not going to be outside of the data set. Kind of defining it technically, what it actually means is more complicated. You have to look at things in the limit and notion of going to infinity in some arbitrary senses, and it's more complicated. But it will basically somehow be where the real data is and not where the outliers are, even if you do this arbitrary thing where you put them all the way up here. Right? It's not going to be perfect, it's not going to be in the middle, but it's going to be something reasonable. And so say if the outliers are not all on one side, it's going to be even better. If it's only 1/3 of the points instead of 1/2 the points, it's going to be even better, and so forth. Okay, so we want to do something like this for linear regression instead. Yeah?
So I was just wondering that when you have a bunch of points, like what is the notion of a median? Like,
Of points in high dimensions,
so like
or in 1D.
what do you mean by a median here?
So median is, so median in 1D has multiple equivalent definitions. So the median in R1, there are multiple ways of saying it. You can just say, assume there's an odd number of points, and then you can say half points are on the left and half on the right. This is one version of saying it. You can also say something like it's the arg min m in R that minimizes. I have a data set here. The sum of the distances, just the distances, the absolute value of the distances. Okay, so not the sum of squares, just the sum of the distances. Turns out this is also the median in 1D.
So in higher dimension, this.
In higher dimensions, this generalizes. This is known as the geometric median. And this, you can also generalize something like this, but there are multiple ways to do it. One, you can say, there's not just two directions. You can say, I want to guarantee that in any direction, I have at least, turns out, 1 over d plus 1 fraction of the points are in every direction, they're more extreme. Or I can say, look at every set of d points, and I can draw a half space through those, or d plus 1 points, and I want the median to be on kind of it's inside of the most of these half spaces. This is much more complicated to generalize, and there are various ways to do it. This is called a geometric median. Might be useful on your homework. And but this one actually turns out to be tricky to solve in high dimensions. But there are kind of ways to do it. Okay, so how do we do this with lines? So there are a few ways to do it. I'll tell you about the simplest one, which has a breakdown point of 0.293. So about almost 30% of the data can be outliers, and this will still be well behaved. That's the Thiel-Sen estimate. Okay, and so what I'm going to do, I'm going to look at a bunch of slopes. And I'm going to be a set Sij is going to be the slope of two data. I'm going to have I'm going to do Yj minus Yi over Xj, Xi. And this will be if I take 2 points and I look at the line through them such that this is such that Xi is less than Xj. Right, so I'm taking 2 of my data sets and I'm drawing a line through it. I look at all the slopes. There are n choose 2 of these slopes. These are always oriented left to right. And then I'm going to set A is going to be the median of Sij in the set S. So I'm going to look at all these slopes and take the median of these slopes. Right, and then I'm going to take B as going to be just the is the median of yi minus a that I've chosen xi. Right, so I look at all the offsets of, given the data point, look at the slope through there, it's going to hit the x-axis someplace and look at the median of these offsets. And that's how I get my B. Right, so the median is known to robust, so okay, let's compute both of these with the median, and this is known as the Thiel-Sen estimator, and it's going to have the breakdown point is going to be 0.293. Okay, and so completely different way of solving this least squares problem, has some advantage in that it's going to be much more stable. It's not optimizing. We haven't set up some cost function and optimized it, but we've fit a line through the data. And this works somewhat well, yeah.
So this new version of median, would it be affected by an outlier as well?
Yeah, but not as much, right? So, of the n choose 2 slopes here, it's going to affect n minus 1 of them. right? So, and of the offsets, it's going to affect 1 out of n of these, right? So if I move a bunch of them, if I move 10% of them very far away, still most of the slopes are going to be in the same area. The same way as in 1D, the median's still going to fit in the right area, right? In the slope and in the offset, right? So I've kind of taken the median twice because I know this is stable. Yeah, there's something called the Siegel estimator, which is doing something kind of similar. It's more complicated, and this gets a breakdown point of 0.5. So you can get an optimal breakdown point for this as well. So you basically yeah, it's you kind of take the kind of do something a little bit different with the slopes, but it's again something like this. So, but you know, this means 10% of the data can be absolute outliers, and I'm still kind of in the right range. Yeah.
I was just wondering that if we have like 2 inverted trees like this.
Of your data, yeah.
Yeah. And we try to find
I mean, kind of like this. This is your data set.
disjointed at the crossing.
Sure. Okay.
It is not. Will it? I'm not sure.
Oh, was this going to find?
The line that will separate these data points.
Yeah. So you know, I'm not sure. Like the best model here is actually 2 different lines, and you don't know which one it's going to be. All of them will find, like least squares, will find something like this. The Siegel estimator, if these are imbalanced, it may be, or that the Thiel-Sen might be fine here. This might be the Thiel-Sen estimator if there are more on this line than there are on the other one. You know, it'll depend. The right thing is actually going to be doing something like a clustering mixed with regression, where you try and assign every points to a cluster based on what the fit is. And then you can find 2 different things and you say, okay, it's bimodal what the fit is, if it really looks like this. Yeah, it could happen, and this is trickier to deal with. Then the model of a single line fitting the data is not the right model, right? So you need to do something more complex if you really want to fit the data. So plot it if it looks like this, or you know, plot the average residuals of the data points and see, and try and figure out if it's a good fit or not. Sometimes you need to kind of look at it after you've fit the model. Okay, so that's all I was going to say about robust estimators. So there are ways to do that which are completely different. What I'm going to talk about now is what's called Tikhonov so regularization. Okay, and so this is also sometimes known as ridge regression. These are the same thing. Okay, just different names for the same concept. And so this is going to minimize something other than the least squares formulation. I'm going to set up a cost function. I'm going to have a new cost function, which I'm going to call L2S. I'm going to take in a data set and a model A. Again, let's assume that I know the offset, or I've even in 2D I've translated, I've added a column of all 1, so now the data points lie in 2 dimensions. It's the same thing, so I just need to, so then I can think of A as a vector. Right, so it could be A and B or just a single thing here. Now I want to minimize yi minus, let's say, A xi squared. So this is the same thing as before, but I'm going to add this term s times the norm of A squared. this will be the 2 norm. Okay, so if A is a scalar here, I just have one slope. We can just think about that, and we'll do another lecture where we'll talk a lot more about the meaning of these things. Let me just kind of give you a brief overview of what this does. So I'm adding this regularization term, and I basically what I'm doing is I'm biasing towards having smaller coefficients. Okay, I'd rather make the coefficients smaller rather than large ones. The reason for this, kind of conceptually, is let's say I've got some data, right, that looks pretty nice, and I want to fit a line to it, and I have an outlier. An outlier is really extreme outlier. Again. This is again for dealing with outliers. Let's say it's really high up here, or it's really low down here. Right? It's either really low or really far, such that this really biases this slope. And so if I do the least squares fit, and so let's look at just the outliers up top here. Right, so let's, it's complicated to think about if it's down here, but let's not worry about it. So if it's up top here, the least squares fit is going to look something like this. The least squares fit. And so that means that it's going to kind of go through the middle of the data, or maybe there's some fixed origin it's going through. But the slope is going to be too high. So I'm going to instead get a different solution here. This is going to be the fit of the ridge regression. It's going to have a smaller slope as the main distinguishing feature, that the slope tends to be smaller. If an outlier is very far in this direction, this helps if it's such an outlier that it pulled the slope to be negative, and then it pulls it back up to be positive. Or if it had pulled it down on this side. So if it's like right here, it might actually make it even worse, but if it's really extreme, then it'll still cause a problem. But it's better to think of it being really high up there. Okay, so then it pulls the slope up, and you want to kind of, on average, have the slope be smaller. It'll keep it from being too extreme, right? And so the other issue is that if you have, remember you're measuring this y direction, and if you have kind of the model is really vertical, then a small change in it is going to cause a really big shift in these residuals, say if you change the x error a little bit as well. Right? If it's really vertical, a small change in x will really drastically change where it maps to in the y coordinate. So also, the more vertical it is, the less stable it is in some sense. Okay, and so think of this as some sort of shrinkage of these residuals. You tend to want to shrinkage of the coefficients here. So the S is a shrinkage term. The larger S is, the more biased it's going to be, and so the less it's going to tend to be more robust to noise in some sense. Okay, and okay, so you're thinking, okay, we had this nice closed form solution. Now maybe we don't anymore. It turns out you still have a nice closed form solution here. It's turned out that the closed form solution is now going to be this vectorized version of the A is going to be X transpose, and this is X tilde transpose X tilde. Right, so this is what the solution was before, and it turns out to fix it, you're going to add this S squared times the identity matrix here inside of this D by D matrix before the inverse. Okay, in 2D, this is going to look like I have this px dot product py, and then on the bottom I have px dot product px. This is the same as the norm squared plus this s squared term here, right? So this is in 2D, this is what the solution looks like. Okay, and so if I was dividing by a term that was like super large, right, or this term was very close to 0 compared to this, I'm adding a little something. It's like I'm not dividing by 0. This is kind of a common trick that shows up. If this was very close, if these were very close to each other, or if this was, sometimes you get other formulations where you're dividing by 2 terms to get the solution, and if this term is very close to 0, it becomes unstable. So if you add some positive bias term, it's always away from 0, and it makes it safe in some way. But this turns out this is a closed form solution for this new formulation. Yeah.
How does this compare to just proving out outliers and running these squares?
How do you know what's an outlier?
I mean, either like obvious measures or no.
Turns out, I mean, there's not always an obvious measure of what's an outlier and what's not. We'll talk about that later in the semester. But this is kind of an automatic way of thinking of dealing with this. Yeah.
So we can iteratively like remove, let's say, some of the points and calculate the cost function.
Yeah, you could try doing that. There's again the question is like at what point do you stop? How do you determine if something is an outlier or if your model is wrong? But if you got the wrong model, you might say something's an outlier when it's not an outlier. Right? So if you, because you have outliers, you can't fit a good model, then what points are you throwing away? Right? So there's sometimes you can show that this will actually work, what you've suggested. Other times it's not so clear because if you had a good enough model, then to know if something's an outlier, maybe you have a good enough model. Maybe you shouldn't trust it beyond that. I don't know. Right, so there's some complications with that effect. This is kind of a well-formulated effect that doesn't have to deal with some of these tricky issues that come up in that approach. So, but sometimes that's the right thing to do. Yeah. Okay, so there's a question of how do you choose S? Well, so again, eventually we're going to, I'll say 2 things about choosing S. So one is we're going to eventually do it again with cross-validation, which we'll talk about later in the semester. But the really interesting thing about it is there exists an S which has variance at least as small as the least squares solution. So there exists a version of this, some choice of S, that has variance of the solution that's going to be equal to or smaller than the least squares solution. So this is kind of a cool thing about regularization that kind of essentially breaks so the optimality of the GaussMarkov theorem. The proof is not too hard. I'm not going to do it. You can basically see this by looking at the residual, looking at the derivative of the cost function with respect to S and show that the slope, that the 0 does not exist in most cases at S equals 0. So that means that you can follow the derivative some amount and decrease the cost function. But it's technical, so I'm not going to go through it here. It's not too hard to see this. So this is kind of a really cool, surprising thing. You break GaussMarkov. Yeah.
So is it really breaking GaussMarkov because the underlying data is biased? So the theorem doesn't hold? Or
yes, so the theorem still holds, right? The data is not biased. The model is biased. You're adding model into the bias. GaussMarkov says the optimal unbiased model is the least squares estimator in terms of the variance. This says if you allow a bias model, this shrinkage regularization term is a bias, then you can get lower variance. So it doesn't break it. It kind of gets around it by examining the assumptions.
Is this like a penalty for lying out, the point lying too far outside?
Yeah, it penalizes, it's not penalizing like points per se, it's penalizing having a really large slope. Think of you're trying to fit a linear model through data and the slope is super high. Think it's almost vertical. That'd be a really bad model to predict the y value. Right, so I'd rather bias towards having a smaller slope, and this is going to end up being kind of more stable in terms of prediction and noise in the data with respect to the how I do on new data.
But then that would depend on how you calculate S, or what is the assumption for this S.
Yeah, so what this says is there exists an S. Sorry, there exists an S with the variance of the estimator being smaller than least squares. So if I choose the right S, I'm going to do better. And how do we choose the right S? We'll do this with cross-validation. I'll talk about, if you don't know what cross-validation is, it's really important. We'll have like most of the lecture on it later in the semester. Okay, but cross-validation will give us allow us to choose parameters like this, and also kind of allow us to predict how well we'll do on new data by holding out some data and using that to kind of train, to kind of choose these parameters. Okay, one more thing I want to talk about in this lecture is a cousin of ridge regression is called lasso, or this is sometimes called basis pursuit. And these are, again, the same thing. And so this is doing something very similar to before. I'm going to set up a cost function. Now I'll call L1 S, and I'll take in the data set and I'll over the choice of parameters A. And this is going to be, again, sum over this, and it's going to have the same yi minus a xi squared, but then the regularizer is going to look instead like where this is the one norm of this regularizer instead of the two norm of it. And you typically don't square it here, doesn't matter.
That's
Yeah. That's A, yes, thank you. Those are right next to each other on my keyboard, so I'm confused. Okay, so it's the kind of the same thing as before, except this L1 regularizer. This one, unfortunately, has no, let's call it simple closed form solution. There is technically kind of an algorithm which, assuming exact arithmetic, can solve for this exactly. It might run an exponential time, although in practice it tends not to. So there is kind of a closed form solution, but it's not the same. I can't just change this linear algebra thing anymore and get the right solution. I need to run like a dynamic programming type algorithm that in some weird cases has, I've seen a paper that works this out, there are exponential number of steps. But it's more complicated. We'll talk about this later in the semester. There's a simple greedy algorithm that works fairly well, and we'll talk about this. Orthogonal magic pursuit, yeah.
I just happen to come across seeing this a lot in practice. Is there a particular reason why a lot of people tend to?
Yes. So the reason this is so popular is that when let's say when A is in RD, right, and D is large, Okay, so the model is I have high dimensional data, I'm fitting a high dimensional model. Then this biases towards sparse A. So sparse A means that many AI are going to be equal to 0 exactly. So that means many coefficients of my model are going to be set to 0, which means that those dimensions of my data I don't use in predicting the value y. And so this is a sparsity-inducing prime. And we'll spend an entire lecture later in class explaining why this is the case and how to deal with this.
Would the optimal solution have many AI equal to 0 or many AI
Yes.
equal to 0?
The optimal solution will actually have many of the AIs equal to 0.
Exactly.
Exactly equal to 0. Yes. Yeah, it's pretty cool. It has to do with the choice of the L1 norm. And if you remember the picture when I talked about the distances and the L2 distance and the L infinity and the L1, has to do with the shape of that L1 norm. There's something very special about it. Okay, so I'll give you a preview that we're going to talk about this, but I'll wait a few weeks to explain this. You can look ahead in the notes if you want to. But it takes a bit to wrap your head around why this works. But you see these particular you see these particular regularizers because they induce sparsity. And this makes your model simpler. This tends to make them more robust. In addition to the regularization properties that happen with ridge regression already, the sparsity ends up being good for other reasons as well. It's simpler to store. It's in other ways it's kind of nicer. Even when this even works, so even works when D is greater or even much greater than N. If you can have way more dimensions and you have data points, it's still okay to do this. Whereas least squares regression, it's usually considered kind of a no-no. Classically, if you take a numerical algebra, like linear algebra course, they say, you shouldn't do it. Here I'm going to say you do it. If you use ridge regression or regular least squares with stochastic gradient descent, turns out it's also okay to do it with D greater than N. But so your linear algebra class probably taught you as a no-no. I'm going to say you can do this even when D is greater than N because of the sparsity effect. And we'll talk more about this later in the semester. Okay, well, I think 2 lectures devoted to these sort of things. Okay, great. Okay, I won't stay very long. I need a campus speaker.
So this is one of the